started. Go ahead, Brian. Thanks.
Great. Thank you so much, Brian. So I'm Brian Sergi at NREL, and I'm going to talk today about the one half of the natural gas use case for Helix. A big part of this use case portion was developing a tool, adapter for a new simulation tool, Saint, which allows for simulation of natural gas networks, and then coupling that with electric power simulation to really explore the intercoupling between those two networks. So we partnered closely with Encoord for this project. They are the developer of the Saint tool, and they were really instrumental in getting most of this use case done. So kind of as a bit of background setting here, gas networks and the electric grid are increasingly coupled. Natural gas provides almost, as of last year, 37% of all generation. And, on the flip side, the power sector itself is a huge portion, almost or a little over a third of total natural gas demand. So these systems are really interdependent at this stage. And that coupling is very good. We've benefited a lot by having a lot of relatively inexpensive natural gas available in the system. That's helped the electric power system be more flexible and reduce emissions, at least in the medium term. But that coupling can also present a lot of coordination challenges, particularly during times of stress. And we see a lot of these in winter periods where there are competing uses for natural gas. We also use natural gas for home heating in particular. And so if demand spikes for that during a winter stress period, that's often also a time when the electric grid is stressed. And so that kind of competition can cause stress on the gas network, which can then propagate to the electric network. So we've seen previous winter events with fuel starvation events where gas-fired generators can't get gas supplies. We also see issues with variability in generators. So gas plants tend to ramp up and down, but the gas network doesn't operate as quickly as the power system does, responds more on the order of minutes or hours, whereas the electric network responds, seconds or below. And so kind of getting those alignment or getting those two systems to align can pose challenges. And the plot I've shown here is just an example from Winter Storm Uri. There were a lot of outages during that, not all related to fuel starvation, but limitations on the gas network were responsible for a big chunk, I think around 12 to 15% of the outages that occurred during that event. So where are the coupling points? There are a bunch of places that these two systems interact. The obvious one is that gas-fired power plants require natural gas to operate, but another component there is they require it at a sufficient pressure, and so they need gas delivered high enough pressures to operate, and so that requires the gas network to be able to supply that gas. There are also other coupling points, like compressor stations can run on gas, but they can also run electricity, and so that's a kind of bidirectional coupling where the two systems are linked. Another example of that is underground storage terminals, which may require electricity to operate. And so you've got, again, this feedback cycle where maybe you would like more gas to operate your electric power plants, but if you don't have electricity to get the gas out of the storages, that can be a problem. As I mentioned, kind of alluded to last slide, electric systems can adapt often in real time. The gas networks take more time to adapt depending on the topology and where compressor stations are located. And so there's kind of this interesting lag between the two systems that needs to be accounted for when you model these as a coupled system. And so, the big message of this use case is that co-simulation with Helix can help us capture these types of interactions and understand how these two systems can impact each other. So the big kind of effort behind this use case was to develop a new Helix adapter for Encoord's Saint tool. Saint is a tool that has a lot of modeling capabilities, but one of them involves a gas network simulation federate that can do dynamic gas modeling. And so we spent time developing a C# adapter to work with Encoord's Saint tool here. We've developed this as a kind of open source Helix adapter, so the code base is available on GitHub. I've got a link at the end of the presentation for those who are interested. And we've also produced as part of that an open source use case with a test network. So folks who are interested in this, there's a 30 bus system, both on the electric side and then also a corresponding gas network, and you could kind of test this adapter and see how those two interact. A really exciting part of this use case was the fact that Saint also has an electric simulator, electric federate that would model power flow. And so one of the things we took advantage of was to use this adapter then to connect essentially a gas and a grid co-simulation, but using both of the Saint tools. So we essentially, this diagram on the right just depicts it, but we stick Helix in between what Saint does in terms of communicating between the electric and the gas network. And this was kind of a unique opportunity to essentially validate how the Helix framework works. So we can test essentially a gas and a grid co-simulation or kind of coupled modeling approach just internally with Saint. And then we can compare that to what happens if we co-simulate via Helix. And it gives us a good chance to not only check if our simulator or our adapter is working correctly, but also to sort of evaluate, how a co-simulation approach stacks up against a more directly coupled model. And we can do this in a pretty, I think, pretty direct way since we're using the same simulators in both of those approaches. So, one of the things that we pursued was to test this across a variety of cases. So we looked at 3 different networks. We had 2 test systems, and then we had a larger system that was representative of the Belgian gas and power system. So this is starting to approach a kind of real system that has real dynamics and is interesting to look at. Each of these systems we tested had coupled nodes where there were gas generators that had minimum delivery pressures. So those were off-takers on the gas network and then providers of electricity on the power side. And we tested these networks for this kind of co-simulation validation against not only a normal operating condition, but also a stress case where we simulated an outage at one of the compressor stations and then tried to see how well that propagated to the electric simulation. So we have a lot of results for this. We actually published this in a paper. I won't talk about all of those here, but suffice it to say that the summary is that the co-simulation approach we built with Helix does a great job picking up the kind of relevant simulator interactions that we were excited about. So for instance, if we see pressure on the gas network falling due to high demand or something, some sort of event on that network, we in turn see the response with the electric system turning down that generator or curtailing output at the generator and redispatching elsewhere. And so the plot on the right is just showing one of the metrics for pressure on the gas network, but comparing the integrated approach with the 2 Saint simulators with the co-simulation approach using Helix, and we got basically identical results across the 2 approaches. So this is a really good sign that we think that our Helix co-simulation tool is capturing again some of the relevant dynamics between the coupling of these 2 systems. And so, one of the last things we pursued here is now that we had this adapter, we were really interested in exploring, what other types of questions can we start to answer with this? And this is where we've been partnering with Kinder Morgan to explore kind of co-simulation of a historical stress event using real gas network data. So they've been great to work with, and they've provided us some data on a historical case where there was a stress event with cold winter conditions and kind of higher than expected demand, gas demand from electric generators. And basically there were some interventions where they were able to deliver that gas, but we explored using this tool, what if that flexibility option was not available? How would that impact electric system operations? And the short answer is we're still working on this result, but the kind of highlight summary is that there is a lot of flexibility that was employed during this stress event that made the system work. But if you remove some of that gas network flexibility, for instance, if Kinder Morgan had not been able to reduce its offtakes to other deliveries in order to get gas to the gas generators, you would have seen either higher cost or some constraint conditions on the electric network. So this is just sort of kind of a preview of the kinds of things that we think we can test with this adapter approach. So just to summarize some of the collaboration and outreach highlights, we did publish a paper on the co-simulation validation approach that's in Energies. We're working on a kind of technical report summarizing that advanced use case that I just talked about, and we've actually also been discussing with some folks at Canary Media about some sort of longer form news article to just talk about this kind of coupling issue more generally. We've had really great engagement with Kinder Morgan on this for applying this co-simulation to real case studies. And then last fall, we organized a panel session at the meeting of the U.S. Association for Energy Economics, where we had a presentation on kind of natural gas and electric grid co-simulation. So to summarize this use case, we successfully developed the Helix interface for Saint. We were able to validate that interface and also kind of explore the co-simulation approach versus an integrated modeling approach. We have published an open source use case as part of that adapter development. I didn't talk about this very much, but we've also been working closely with Karthik and the folks at ANL to present this framework in a way that's sort of consistent with other work to make a kind of more generalizable domain API for gas and grid co-simulation. So that's something I'm happy to talk with folks about more. And then finally, we've started to at least apply this adapter to an advanced use case that actually looks at how we can use this tool to learn interesting things about the state of gas and grid coupling. So with that, I've got a couple of reference links to some of our GitHub repositories or the papers, and I'm happy to take any questions for the remainder of the time. Thank you so much.
Thank you so much, Brian. That was a great presentation and a lot of great work from you and the team. Great job with all that. And yeah, we do have time. We've tried to give ourselves 10 plus minutes for question and answer. So we have a chance to kind of dig in further on all these exciting results. Feel free to just come off mute and talk, or if it's easier, you can type a question in chat or raise your hand. I have a starter question for you. You talked about a number of different networks sizes that the testing was done with, and I was wondering if you could dive in a little bit more into kind of some numbers around that. Like how many nodes are there on the gas and grid side for each of those test systems, and were there any scalability considerations you ran into as you were working through those?
Yeah, I'd have to actually go look at the paper. I think the test network, I think, is the 30 bus case on the electric side and maybe like a 24 or 26 node on the gas side. So that's pretty small. The Belgian case is, on the order of 100 to 200, I think, nodes. I don't think we didn't see too much scalability problem. I mean, the Belgian case took a little bit longer to solve, but it was still I would say like minutes. Now we were only running a day of a simulation here, so I think there is a question of start to look at maybe you want to simulate a whole year of operations, and that might get more interesting. I think the other part that's something we started looking at, didn't focus on too much, is that the co-simulation approach that we really looked at was one directional, so the gas offtakes from gas-fired generators. And not things like you have electric compressor stations on the system that they're on the gas network, but they require electricity. So that's a bidirectional coupling that I think would, increase the complexity and the solve times and probably the number of iterations you need at each step. So that's, we didn't have a system with those relevant parameters, but if you did, or if you started to be interested in those, I think there's probably interesting scaling questions that you'd have to think about.
Great, thanks. Looks like there might be a note or a question here in chat. Can read that out for folks who are on audio. There's a question that says from, I apologize if I get the name slightly wrong, but Abhijit asked if you're using a hierarchical broker or a single broker in the use case.
Yeah, we were just using a single broker. We had two federates in this case, so it was pretty simple. I imagine you could have subpartitions of either of these networks, and then start to build out more of a hierarchical structure where you had multiple brokers and controlling multiple federates. But in this case, we didn't need to do that.
Yeah, thanks. Abhijit, I don't know if you had any, want to come on mute with any other questions? Oh, no, I see you. Thanks, great. Other questions from folks in the audience?
Hey, Brian. So what level time step did you have to implement to make sure that the response was realistic?
Yeah, so the gas networks that we've run with, the way that I think users often run them is like 15-minute time step, where they solve it every 15 minutes, but they're also kind of adjusting or ramping up through that 15 minutes. So we think we solved at 5 minutes, but then the gas, I can't remember if we had to update the gas just every 15 minutes, essentially, with what the electric demand was. I think that was the time step we used. But we were also not doing, so this was, yeah, I guess an AC power flow on the electric side, and we weren't doing, dynamics and things like that. So it was more of like the scheduling problem than it was looking at those aspects on the power system.
Okay. And then were you able to implement any, were you looking at any resiliency or like change in control structures, or was it an impacts analysis?
When you say changing control structures, what are you thinking about there?
So like you said that there were some reserves that helped resiliency in a high gas use case in real life, but were you able to implement some of those reserve methods in your simulation, or were you just looking at impacts of shortage scenarios?
Oh, yeah, okay. Yeah, it was more impacts. That case, well, it's actually interesting. It's not really a reserve case. It was a case where the electric generators asked for a certain amount ahead of time. So that was what was scheduled. And then when the time came, they asked for much more than that. And so the gas operator essentially kind of created more space on the network by foregoing some sales to other people that were, I guess, not as high a priority, so they could defer transfers that were planned to other third parties in order to deliver. So what we did for that advanced use case was just to model that kind of flexibility of saying, okay, you don't have to, like, you had scheduled deliveries of X to these other consumers. What if we allow you to relax that? How much would you actually send to the gas network? So that was the way we approached that. And so I think the answer to your question is it's a bit more of a impacts analysis and not an explicit, you have like all these options on the table. But I think you could do that with this approach if, a lot of these, I think it just depends on what you put in your simulator. If you specify that as a hard constraint, or if it's a soft constraint, you allow it to be relaxed at some penalty or yeah, something like that. I don't know if that totally answered your question, Nadia, but
Yeah, thanks. That makes sense. And then the multi-million-dollar question: do you think this could help in Texas during their more frequent winter storms?
yeah, that's a great question. I don't know. I think that yes and no. Like, I think this tool could do some interesting things on how these systems interact. I think probably the biggest challenge going forward is what is the data quality and what can you anticipate? So for instance, the Texas case I mentioned, I think like 12 or 15% of the outages were fuel starvation, which I think could be well modeled in this kind of approach. But the fuel starvation events were caused by gas wellheads freezing, and I don't quite know how to put that into this model in like advance or a priori. Same thing with like a lot of the generators just froze, and so that wasn't like a gas delivery issue. Is they got cold and froze. And so like I think the biggest challenge is how do you anticipate what those possible failure routes are, and then have the right data to kind of say like, well, this is a reasonable outage case. So I think it could be applied for that, but the challenge going here, I think, or going from here is getting good data and getting good scenarios to test and assigning some reasonable level of uncertainty or probability to those and that kind of thing.
Yeah, this is Trevor, kind of a follow-up to that. So like if you wanted to do contingency analysis kinds of things for a winter storm like that, it sounds like you're saying modeling those is not hard, anticipating what those contingencies might be is trickier.
I think that's right. Yeah, because I just think for the winter storm case or in Texas, for us, like our gas model has like essentially inflows and outflows, right? So the inflows are gas producers supplying gas, and we can set a variable to what that is. So you could easily say, okay, what if it were reduced by half, for instance? I'm just wondering if, right before that winter storm, people would have thought, okay, gas wellheads might freeze, so we should cut off, like producers won't be able to supply the gas system.
Sure, yeah.
My guess is like we are thinking about that now because it happened, but we might not have thought to put that in the model before Winter Storm Uri. I don't know. This is where probably people who are more versed in the gas side might be able to say like, yeah, we thought that could happen. We just didn't translate it to the electric side. In which case, I think this tool helps do that if those two communities start kind of playing with the same tools and talking to each other.
One thing that occurred to me with this conversation is that it could be that a tool like Saint has some more capability built in, but it could also be an opportunity for there to be an additional federate to join the party if somebody had done that work of like, what are the different outage patterns for different extreme events? In the future, certainly people would be paying attention to freezing and perhaps have some labels on which, probabilities of failures of different facilities from that. You could imagine similar sort of overlays, which you're right. It seems like you need to get an extra group of folks in, whether it's the gas team or folks who are thinking about disasters and maybe them getting together. But, I don't know if if the hooks are around so that you could, with not too much effort, have that information come into, say, the Saint model and say, oh, well, look, this just happened, and kind of play those types of outage conditions back.
Yeah, I think that's actually really right, Brian. I think I won't speak too much for encoord, but I think that one of the reasons they were excited about this is, not just from the gas and electric side, because they have both of those pieces, but now because those are hooked up, you could bring other things to the table. So you could have some sort of, other federate that does maybe some very useful demand response, and that demand response translates into changes in your power system operation, which then propagate to the gas side. So I think that's why that they were really excited about this kind of Helix framework, because it will hopefully open the door to connect to some other interesting stuff.
Great. I think we have time for one more question. Could be two if they're really quick. Feel free to raise your hand or put something in chat. In the meantime, I'll ask a quick one. That was a follow-up on Nadia's first part of her question, which was the idea of like with a 5-minute time step, you're certainly in the scheduling and not necessarily physics level dynamics part of the power grid. But my understanding, and I was wondering if you could elaborate on it, is that the gas network that does start to be actually in the sort of faster dynamic time frame when you start to look at the pressures and changes. Is that right, or can you elaborate on that a little bit?
Yeah, it's definitely a dynamic model, but I don't think it's faster, because I think that there's a slower response time for instance, you start injecting at some node above in the top of your system, that takes time for then the rest of the system to kind of catch up, like for the line pack to change, or for compressor that's downstream to change, or to see kind of a difference in its operations. So I don't know. I see that Sule is on the line, so he's worked with us at Kinder Morgan. He might have a more insight on there. I don't know, Sule, if you have interest in saying anything, but my sense is that the time response is like, I think 15 minutes is often used to model the gas system, and the changes can evolve over even slower pace than that.
Yeah, I think Brian, you've clearly indicated the slower dynamics in gas network. You look at a gas molecule travels about 50 miles per second. So taking that into consideration is not as milliseconds travel time for the electric network. So it's a little bit slower. So in terms of being able to capture line pack difference and pressure difference, 50 minutes to an hour time simulation is probably adequate enough to capture the gas dynamics. So you're correct.
Cool. Yeah, that's very helpful. So it's kind of a neat combination of like dynamic scale on the gas side, and then a little bit, in this case, more steady state on the grid, since those are that couple of pieces. But yeah, that's a really nice. We've reached the end of our question and answer time here. So please join me yet again in thanking Brian, and also thanks Sule for weighing in there. I'm going to go ahead and stop this recording, and in that transition time, we can also get Karthik up for our next presentation.